Today we are going to see a back propagation. This back propagation is used in neural network training. While training, we have to adjust the parameters of the network, and this adjustment is done in back propagation. We can see it in detail. So before moving on to the back propagation, we should understand the working of a neural network. Okay. So here we have these circle shaped things. These are the neurons or the nodes, and here are three nodes over here. There are one node and here one node, and these nodes are connected with the edges. Okay, and the input is given to this layer, and the output of the network we get from this last layer. Okay, so each one is called as a layer, and the first one is this is layer 1, layer 2, and this is layer 3, and so on. Okay, and we call it as an input layer, and this is an output layer, and in between input layer and output layer we can have multiple layers, and these are commonly called as hidden layers. Okay, and the inputs to the neural network will be given to this nodes, to these nodes. Okay, so let us give x1, x2, x3. So assume we have three inputs, and it will be given to this thing. Okay, then each edge will have a weight. Okay, all these are weighted edges, and let's give the name like w1, w2, w3, and w4. Okay, these are the weights for these, just like weighted graphs. In weighted graphs we have edges with the different kind of weights. Okay, here also we are using the same concept. Okay, and this will be the weights, and the output is labeled as y cap. Okay, so this is the predicted output of our neural network, or the output calculated by the neural network. So for example, you are giving we have the neural network to identify, we give an image to the neural network. Okay, so if we give the image what is x1, x2, x3, those are these will be the pixel values of these images. Okay, and if we have a 10 into 10 image, 10 into 10 pixels, that is 100 pixels, then we will have x1, x2, x3 up to x100. Okay, that's many input will be there to the network. And the purpose of this network, assume we input some kind of image to the network, and the network has to find out whether it is a cat or not. Okay, whether it is a cat or not. If the image is of a cat, it has to give output 1, that means it is yes. And if it is not a cat, it has to give the output 0, that means no. Okay, so if the output is 1, it means that we have inputted an image of a cat, and if it is 0, that means like that. So how the network will find that it is a cat or not? So in order to find, first we have to train the network. Train the network means we have to give appropriate value for these weights, and there is one more parameter called bias. Okay, so we have to give appropriate value for weights and bias. So that is what is meant by training. Okay, so in order to set appropriate value for weight and bias, there are some steps. Okay, so we do the back propagation for this. Okay, so we are giving an image to the neural network, and it will give you 1 or 0 as the output. So what value we get from the neural network is labeled as y cap. Okay, we call it as the predicted value. And we have the original value y. That means if we have an image of a cat, the y value will be 1. If the image is not of a cat, if it is a flower, the y value will be 0, like that. So we have a label data over here. Okay, so we have n number of, suppose we have 10 images over here, and for all the 10 images we know this value, what is the y value. That means we know that whether it is cat or not cat. So based on this value, based on this non data, we are training the network. Okay, so y cap is the actual value or the expected value or the expected output, and y cap is the output given by the network. Okay, so what is our purpose? This should be same. These two should be same. That means the network should give you the expected value. This is the expected value. Okay, this is the expected value. So when we input this image, this is the expected output. When you input this image, this is the output, expected output, like that. Okay, so if it is not giving one, what should be done? You have to make changes in these weights and biases to get the output as 1. Okay, so this is the y is the actual value or the expected output, and y cap is the output from the network. Okay, or the predicted value. And we have to find out the difference between this y and y cap, and we call it as loss. Okay, loss is equal to y minus y cap the whole square. Okay, so we generally call it as mean square error. Okay, and in the training process we have to follow these steps. That is, in order to set the appropriate value for weight and biases, we have to follow these steps. The step 1 is in forward propagation. The first step is called forward propagation. That means that we give input the values of x1, x2, x3, and we start with some random values for w1, w2, w3 and w4. Okay, and this will find out, this network will find out some value. It will calculate some the value of y cap based on these values, based on x1, x2, x3 and w1, w2, w3 and w4, and based on bias it will calculate y cap. Okay, so that process is called forward propagation. So calculate the value of y cap. It is a function of wi, that is weight, xi, that is input, and bias. Okay, so this is the function. Okay, then step 2 is find the loss. Okay, once we got the value of y cap, we have to compare it with y, that is the expected output. Okay, so loss is y minus y cap the whole square. If we have only a single data, this is the equation of loss function. And if the loss is very high, that means we are not getting the expected output. Okay, the neural network is not giving you the expected output, then the loss will be very high. So at that time we have to adjust these parameters, especially this w and b, weight and bias, we have to adjust. So the loss is high means the predicted value y cap does not match with the actual value. So what should we do? We have to do the back propagation to adjust the weights and biases. So W new is equal to, that is how do we adjust the weight? The new weight value will be equal to the old or the existing weight value minus eta into dou L by dou W old. Okay, so W old means what is the current value of W, that is W old. W new means what should be the next value of W. Okay, and here eta is called learning rate, and normally its value is set to 0.001. It's a small value, eta, and dou L by dou W is the derivative of the cost function or loss function with respect to the W value. Okay, and based on this derivative we identify that whether the W has to be increased or to be decreased. Okay, so that means that if the derivative is negative, we will increase the weight value. Okay, that means this equation will become W old plus eta into, like that. And if it is a positive value, we will subtract some amount from W. Okay, So that means that if the derivative is positive, we will decrease the weight value, and if the derivative is negative, we have to increase the weight value. That's how we adjust the weights. So after updating all weights, so we have to apply this equation to all weights. That means we have 4 weights in this particular example, W1, W2, W3 and W4. So we have to do this operation for all the 4 weights. Okay. Then after updating all weights, we have to go back to step 1. Again do the forward propagation, find out y cap and find out loss. And if there is a big difference in or it is a high value, if it is high, we have to again do the back propagation. So it goes on till we find the optimum value. Okay. Then in back propagation, what we do? So this is the network we have. Okay. And the loss function, and we have y minus y cap the whole square. Okay. And we have to update the weight value. W4 will be updated like this: W4 minus eta into dou L by dou W4. Okay, so based on this derivative, we will increase or decrease the W4 value. And similarly, W3 is like this. The new value of W3 will be W3 minus eta into dou L by dou W3. Okay. And similarly, W1 and W2 will be adjusted like this. Okay. And after updating all these 4 weights, we have to again calculate y cap using the input data. And again, if the loss is very high, we have to go for another back propagation like that. Okay. So if we have a set of input output data, that means if we have multiple data, and normally in machine learning we have thousands or millions of data, and if we have multiple data, we call it as a cost function. Okay, we can call it as a cost function or loss function itself, but the function will be like this. Okay, sigma is equal to 1 to n y minus y cap the whole square, or even the average. We can take the average also as the cost function. So we have to find out, we have to input all the inputs, and for each input we have to calculate the y cap and find the mean square error. Okay, take the sum, and we can find the average. Okay, you can find the average also. So that is the procedure. And this is the equation to update the weight value. New weight value is equal to W minus eta into dou C by dou W. So C is actually the cost function. Okay. So what does it mean? If we make any change in W, how it affects cost? Okay. If I increase W, what happens to C? So rate of change of cost with respect to weight. Okay, that is the meaning. And this part is actually the gradient. Okay, the gradient is the rate of change of cost function with respect to the weight. Okay, so this is the gradient we have to calculate, and assume the cost function. So this is the cost function given. Okay, and on the x-axis we have the weight, and on the y-axis we have the cost function, cost. Okay, then this is the minimum value. And how do we reach this minimum? Okay, suppose we have started with a random value over here. Okay, the weight value, initial value of weight is some random value. We randomly choose some value for weight. Okay, suppose the random weight we have started with this. So how do we find out whether we have to increase or decrease the weight in order to get the minimum value? So we find the derivative at that point. We find the slope. Okay, and if it is a positive slope, this is a positive slope. If it is positive, we have to, if it is the positive slope, we have to reduce weight in order to get the optimal solution. Okay, and if suppose the point was here, if the initial value was here, or if the weight value is this, when we calculate the gradient, we find that this slope is negative. So when the slope is negative, we have to increase W to get the optimal solution. So we'll increase, we'll get somewhere here. So again we find the derivative. Okay, slope, this is again a negative slope, so again we increase W, so we'll get it somewhere here. Again calculate the slope. Like that we can move forward and finally reach the minimum. And similarly here, since it is a positive slope, we have to decrease weight. Okay, so we will decrease weight. Okay, weight will move in this direction. So finally decreasing, finally we can reach the minimum value. So that is based on this value, dou C by dou W. Okay, this one, dou C by dou W, we decide whether to increase or decrease the weight. Okay, so that's how we adjust the weight and finally reach the minimum. So in the previous slide we have seen the very simple neural network. Okay, and in practical applications the neural network will look like this. Okay, input layer has multiple neurons and we can have more than one hidden layers, and in the output layer we have more than one neurons. Okay. Okay, neurons are perceptrons. Okay, so this here there are 3 hidden layers. We are giving input to this layer. So in this you can see that every node in one layer is connected to every node in the next layer. Okay, so this layer is connected to all the layers. Okay, all the nodes in this hidden layers. You can take every node. So if we have 8 layers over here, 8, we have 8 nodes over here, and we have 3 plus 3 is 9 layers over here. So we have 8 into 9 edges are there in between this input layer and the first hidden layer. And similarly here we have 9 into 9 edges, and here also we have 9 into 9, and here we have 9 into 4. Okay, that many weights are there. So for every weight we have to calculate this dou C by dou W, and based on that factor we have to update the So how do we adjust, or how do we find all these derivatives for a particular weight or for all the weights? How do we calculate the rate of change of course function with respect to the weight? So let us, this is a complex network. We can take a simplified one. Okay, so this video has been taken from this YouTube video. Okay, just watch this one. How do we reduce? We want to reduce a neural network, or we want to get a simplified network to give the explanation. Okay, so suppose this is our network. Okay, so this is our entire network. We want to get a simplified version. Assume that we have one node in all the layers. Okay, we are just squishing it into a single element in each layer. Okay, and these nodes, the weights of these edges are W1, W3, W2 and W3, and the biases like that. Okay, so we are taking a simplified view of this network. It is not equivalent to the previous complex network, but in order to just understand the concept or how to find out the derivatives, we take a simplified version. That's all. Okay, so we assume that there is a single node in the input and a single node in the first hidden layer, single node in the second hidden layer, and a single node in the output layer. Okay, just for simplicity we have taken like this. So in practical application we cannot do like that. Okay, so the simplified network I have drawn it here. Okay, so one input node, then two hidden layers, okay, one node each, then one output node. Okay, and the activation functions in these nodes are H, G and F, and the weights are W1, W2 and W3, and for the time being we are not considering biases. Okay, and the cost is this one. Cost is a function of F because the output is y cap. Okay, and how do we calculate this one? Y minus y cap the whole square. Okay, it's a mean square error. This is actually, this is a constant one as far as the training set is concerned. So this is the variable part. Okay, so we can say that the cost is depending on y cap, or cost is a function of y cap, and y cap is actually this f, function f. Okay, so we can say that the cost is a function of f. Okay, or cost is depending on f. And what is f? F is depending on this previous activation function g and this w. Okay, w3, and g is depending on h and w2, and h is depending on w1 and the input value. Okay, it goes like that. And here we have to apply the auto differentiation. We have to find the derivatives starting from the output layer to the net input layer. Okay, in this direction we are going to find out the derivative. So first one, we are going to calculate the derivative with respect to W3. So we have to find out dou C by dou W3. Okay, dou C by dou W3, and C is depending on F. So first we have to find out dou C by dou F. Then F is depending on W3, so we find dou F by dou W3. Okay, that's how we apply the chain rule over here. Then we have to find out the derivative with respect to W2. Okay, that is dou C by dou W2. So in this path we have dou C is depending on F. So we have to find out dou C by dou F, and dou F is depending on G. So dou F by dou G, and dou G by dou W2. Okay. And then for the last one, dou C by dou W1, dou C by dou F by dou G, and dou G by dou H, and dou H by dou W1. That's how it goes. Okay. So in this way, we have to find out the weight derivative for all the derivative with respect to all the weights. Okay. Now we consider another network which has multiple nodes in hidden layers. Okay, so here we have two hidden layers. In hidden layer 1 we have two activations, H1, H2 and G1, G2. Okay, like that. So how do we calculate? I want to find out the derivative with respect to W11. How do we calculate it? Okay. So before finding out this, you check whether there is multiple paths from this W1 to the output. Okay, so here from W1 through H1, G1, F, okay, we can reach the output. And there is another path H1, G2 and F. Okay, so there are two paths. Okay, so we have to, when we find the derivative, we have to consider these two paths. Okay, so first part is we find the derivative in this reverse order, dou C by dou W1. So C is a function of F, so dou C by dou F, and dou F by dou G1 into dou G1 by dou H1, and into dou H1 by dou W11. Okay, that is the first part. Then we have to find the summation with the next path. Okay, that is dou C by dou F by dou G2, dou G2 by dou H1 by dou W11. Okay, If you have one more path from W11 to F, we have to find the sum with that path also, derivative from in that route. Okay. So in this case, we are actually applying the auto differentiation. So in the first layer, we find out this one, and in order to find the next derivative, we just multiply it with this one, like that. Okay. So that is all about the backpropagation and how we update the weights in the neural network. Okay, these are the references. This Michael Nielsen's neural network and deep learning, it's a wonderful material. You can refer that, and these YouTube videos will also help you to understand this concept. Okay, they have given some graphical visualization, so that will be helpful for you to understand. Okay, please refer all these four references. Okay, thank you.